Exactly right. This is Lagrange's identity at work. See, because Lagrange's identity trades the difference of these, ULV minus VLU for the derivative, the total derivative of this. So you've got two of these. You're fine. Yeah, you're awake. Okay. So what I'm saying is you've got, I think over there. Well, it's definitely this. Oh, it's exactly that, right? So this is the total derivative of that. So when you take the integral of the total derivative, you just get this, fundamental theory of calculus, value from here to here. Then what?
Or the conjugates, oh, they're real. Or no.
He says, all right, he says, we will show that the last term in the preceding equality vanishes for both regular and singular systems. If P of A equals to 0, the result follows immediately. If P of A is greater than 0, then and U and V satisfy boundary conditions of the form that we've been studying, then it forces the thing in parentheses to be 0. All right. So anyway, I'll say read page 252 if you don't mind. There's a pretty straightforward reason this is 0. Obviously, if P of A is 0 and P of B is 0, then great, you got it. Oh, I've erased that part, so I don't know anymore. Well, all right. Let me get on with that here because I don't want to run out of time. I want to get the punchline in here before I run out of time. We may already be out of time. I'm sorry. If you need to go, let me know. Theorem 5.9.10, right, is that eigenvalues are real for this Sturm Liouville system, right? How do we know that? Well, we just proved it was self-adjoint.
Oh, right.
So it has real eigenvalues, right? And then his next result, but there is an interesting calculation I should not skip over. In fact, this was one of the things I really wanted to make sure I said today. Let me not skip that calculation. I mean, yeah. So you're like, well, why does he give a proof? We already knew that. The reason he gives a proof is that the calculation in the proof is interesting. All right. And when I first saw this a couple years ago when I was teaching some students like yourself who wanted more differential equations, actually, and they just wanted the boundary values in differential equations class. That's where I first discovered this. I mean, I probably, if I paid better attention in other classes I had as a student, I would have heard it before. But anyway, here it is. So again, whoa, you're okay. So we've got LU equals to minus lambda omega U implies lambda is real. And so the fact that lambda is real, again, it's a self-adjoint operator. So I guess, have we proved? What was the fine print there for the self-adjoint operator? On a what? I don't know. I'm a little, I guess I should be not so nonchalant. Maybe I'm forgetting the, maybe we're not, have we earned the context to use that theorem, I should worry a little bit. But here's the calculation. We have 0 is equal to LU U minus ULU, right? So this right here is by the previous theorem, 5.98, that it's self-adjoint, right? And then what do? You trade your LU for minus lambda omega U, right? And then you got your minus U minus lambda omega U. And what do we got? Well, then we get a lambda bar minus lambda, parentheses, times, well, let's see here. It looks like, How's it go? I guess it's omega u, u. Oh, man. What do we know about omega? Was omega was real, wasn't it? I think if it's a real scalar, you can move it. I believe it's positive, so it's real, which means I'm allowed to move it from the from here over to here, right? For this inner product.
Yeah, it's so.
I mean, really, you could more to the point.
No, it's not all the way. Yeah, yes.
More to the point, I could.
It's its own conjugate, so yeah.
Oh yeah, I shouldn't. Well, I can't just pull it out though. That's not something I can. This is not a constant, right? I think I can do this. Yeah. Maybe I better just write out that these are both equal to. I see why he hasn't written things. I understand now why he hasn't written certain things. Integral from A to B.
The inner product is
the
conjugate of it's symmetric basically. So I guess you can just.
Right. I mean, they both of the inner products work out to that, with either a lambda or a lambda bar. So you can write that, and of course this you can rewrite as lambda bar minus lambda integral from a to b of omega of x, modulus of u of x squared. Great. He says, but omega of x is positive, so the integral is a positive number, therefore lambda bar equals to lambda, and that completes the proof. And then the next thing he proves is that the eigenfunctions corresponding to distinct eigenvalues of a Sturm Liouville system are orthogonal with respect to the inner product of the weight function. Now that is interesting. That's the one I was thinking about. Next up, theorem. If Lu equals to minus lambda 1 omega u, and Lv equals to minus lambda 2 omega v, where lambda 1 is not equal to lambda 2, all right, then the inner product of u and v, and let me put a little sub omega here, is equal to 0, where what I mean by that is we integrate from a to b of omega of x times u of x v bar of x dx. And then the proof is a little lengthy, but so I'm not going to go through it because we're kind of out of time. But the proof is straightforward. The proof, I should emphasize, the proof here is straightforward. The interesting thing is that the orthogonality. There's another geometry that appears here. It's a geometry which reflects the omega. Where's this omega coming from? It's characteristic of the Sturm Liouville problem. So you actually are like defining orthogonality paired to the differential equation that you're given. So your concept of what's orthogonal changes according to which weight function you have for the different differential equations. It just so happens that the weight function for a lot of the examples we've looked at has been 1. So like sine and the problems that had sine and cosine as the eigensolutions, the weight was 1. So you couldn't really see the distinction between the orthogonality with respect to the usual like L2 inner product versus the which you might call the Sturm Liouville inner product or something.
Interesting.
Yeah. And so this to me, I was like, oh, it's so cool. Like the differential equation itself comes like with this new world of geometry in which you have to understand the solutions and how they behave and interact. But to me, so you ask the question, why are we studying? Maybe you should ask the question, why are we studying, orthogonality? Why are we studying self-adjoint? Why are, all these different ideas? And the answer in part is because they help you understand what's the general pattern for this whole list of partial differential equations we've been looking at. Like the structure of the solution sets, they resemble one another. And the reason for that is they all have this underlying same theory of like the Sturm Liouville theory. And this for that class of examples. And then of course you can there's modifications of this. Not everything is Sturm Liouville, but Sturm Liouville casts a very wide net. And so let me show you some things on the projector, because I think, oh yeah, perfect. So that was the end of the Sturm Liouville section. The next thing up is inverse differential operators in Green's theorem, which I will talk a little bit about today, just to get us started. But I won't. We'll. The next thing I think we need to talk about. Well, see, I'm torn, because there are two paths to go down next. The one is to do Fourier transforms next time. The other is to do distributions next time. I'll have to think about it. And by next time, I mean Wednesday, of course, because I gotta, I'm not gonna lie. Well, I am going to lie to you on Monday. Sorry. Stupid joke. But anyway,
Oh, yeah.
my bad. One second here. Where'd it go? So, and I'll share these. I'll share these. I'll share this with you as well. Okay. When I get back and think about my life here, where do I want to save that? I want to save that in my files. What class is this? This is Hilbert Spaces, right? I got a folder for you guys somewhere in here. Oh, there it was. All right. So this is the book that I used in part with those students I was talking about. This is, I recommend this book a lot. It's a nice thing to have around, and you can get a third edition of this thing for like $10. It's well worth having a copy of it. I'm just going to show you some high points from this. So like here is, for example, his litany of results for if you're dealing with this stupid thing, and it keeps like static electricity or something. I don't know what's going on here. So here's his, if you're dealing with this boundary value problem, if you have these boundary conditions, you get this. If you got these boundary conditions, you get that. If you have the periodic boundary conditions, you get this. So this is a really nice summary of the three examples that I've talked about, in detail. And he actually also has down here how to find, to calculate the Fourier series to fit the initial condition or whatever. These are the integrals you do to find the coefficients to fit your solution to the. That's kind of cool. And then he also has a discussion of the Sturm Liouville problem. All right. Now this is not as sophisticated a book as the one we're using. This is a lower level book, but it also has a lot of like hand-to-hand combat arguments for. So this is a book you'll find a detailed derivation of how do Fourier series work, like the convergence or divergence of Fourier series is dealt with somewhat concretely in this book. It's nice for that. So like here's some examples of Sturm Liouville problem. This one we talked a lot about. This is heat flow in a non-uniform rod. This is vibrations in a non-uniform string. These are all Sturm Liouville problems, And circularly symmetric heat flow. I think I showed that one to you. Here's some further, discussion here. Terminology. Fixing it to zero, that's like a fixed temperature condition if you're talking about heat flow. Derivatives being zero means insulation. I won't talk about this. For vibrating string, if the derivative is zero, it means the string is free. But anyway, I think this is just a nice collection of, And in this book, instead of omega, he's got sigma. So keep that in mind as we go on here. So his weight function is sigma rather than omega. And let's see here. And here's pretty much everything we said today and a little bit more, all in one nice place together. So for the Sturm Liouville problem, the eigenvalues are real, and there exists an infinite number of them. They can be sequenced like that. There's a smallest one. There's not a largest one. The eigenfunction's unique up to an arbitrary multiplicative constant. Oh, that we didn't, hey, we didn't get this one. It has exactly n minus 1 zeros. Well, that we did not see in this book, did we? So they form a complete set. Set. Not system. Meaning that any piecewise smooth function can be represented by the generalized Fourier series of eigenfunctions, like so. Almost everywhere. There you go. Furthermore, the infinite series converges to the average of the jumps if it's a jump discontinuity. Eigenfunctions belonging to different eigenvalues are orthogonal in the sense of the weight geometry. See that? That's cool. That's what we were just talking about? Yeah. And any eigenvalue can be related to its eigenfunction by the Rayleigh quotient, which is this integral right here. So, yeah, when I took my course in boundary values and PDEs, we did a lot with. He talked a lot about this. I don't know. I feel like I had like 7 lectures that all derived this. Like, I don't know. But anyway, let's see here. What else we got? So I scanned some representative pages for you guys in here because I thought it'd be nice to read something that's a little bit more wordy about this stuff if you're interested. And so this is definitely that. And this is essentially I'm advertising this book to you guys because it is nice. And so here's his section on self-adjoint operators. Let's see here. I think we've done a lot of these things today. So Lagrange's identity. There's the differential form of Lagrange's identity. This is actually called Green's formula. This thing we did, the integral. That's actually Green's formula. And let's see here. It is equal to 0. Ha! Ha! That's what I said. So, great. What else do we got in here? So anyway, I will share this with you guys. Just thought it'd be, if you're interested in, reading and getting a second opinion on this section, this is pretty nice, I think. What? Hey, I didn't do anything. Don't you? Yes, the eigenvalues are real. Let's see here. Unique eigenfunctions. So anyway, all the proofs in here are a little bit more detailed. Yeah. And he even has a word here about how to do Gram-Schmidt orthogonalization has to be done. If you're doing it for one of these, it's got to be done with respect to the weight function. That enters the enters the scene, All right, so the other thing I wanted to show you, I got this out here. So one of the things that's deeply fascinating about studying these problems is that this book does Lagrange's identity in one dimension, like I just showed you, but it doesn't stop there. Because there's also Lagrange's identity for like 2-dimensional and 3-dimensional problems, and then the Green's formulas have actually something to do with the Green's theorem that you know. I don't like to look at it like this. I need to change my default. There we go. So this is later in the book, chapter 7. So now he's replaced, before it was the second derivative with one variable. Now it's the Laplacian. So that could be partial x squared, partial y squared, you know, some of them, or it could be the three-dimensional Laplacian, I mean, whatever. And so that's, but that's essentially the, you know, the same, that's the Sturm Liouville problem, essentially. Really? Come on. Oh. Golly. Anyway, that's called the Helmholtz equation. And here's the corresponding theorem. The eigenvalues are real. There's an infinite number of eigenvalues. There's a smallest eigenvalue, but no largest one. But now there may be many eigenfunctions. But there's still some sort of complete set. There's a generalized Fourier series of eigenfunctions. And I think if you really look at what I had showed you at the start of today, the Laplace's equation for 2 dimensions, this would be an example of that kind of thing. Let's see here. There's a Rayleigh quotient. But now all of the integrals are actually, honest to goodness, they involve like area integrals, and this is a line integral, you know. Let's see here. So, where was I? So yeah, that's pretty much all I got to say about the Sturm Liouville problem. I think it's really interesting that, I think it kind of gives you an answer in part for why were we studying these things to start with. It's because it helps us to understand how to solve differential equations more deeply. If nothing else, like that's a huge benefit. So one of the next things on our docket here, and I'll just get started briefly, because since I got this open, I want to go through this right briefly. And I'll give you a link to this. But one of our next topics, either next topic or topic after next, is so-called Green's functions and the so-called problem of inverse operators. So, you know, we were looking at the theory of a Sturm Liouville operator, right? And so, generically speaking, if you've got an inhomogeneous problem, you're solving something like L of y equals to f, right? And we know from differential equations that we can build the solution as a sum of the homogeneous and the particular function, right? So it would be nice if we could find an inverse operator where you could just say, well, my solution is L inverse of f, right? But unfortunately, you don't really mean inverse, right? Because you already know that there's an infinity of, it's not a unique solution, right? I mean, there's that whole homogeneous. So at best, you could hope to find something that is giving you like a representative of the equivalence class where equivalent solutions have the same, differ by a homogeneous solution, perhaps, something like that. And, well, that can be done, essentially. So the first thing you could do that for would be a first order problem. You're trying to solve, you know, the y prime plus, this is the linear first order problem, right? And, you know, we can solve it by the integrating factor method, beep boop ba boop, and we get this formula. So if you look at this, this is telling you in some sense the inverse operator, see, because if I'm feeding so p is given, but q is variable in this thinking. So if you're trying to solve it for q, what do? Well, you integrate q against this function k, where k is the exponential of the difference of these integrals, right? And so that's an example of what's called Green's function. This is Green's function. Green's function, the integral of Green's function gives you the inverse operator to the differential operator. This is, roughly speaking, the idea. So that's the easiest case, one-dimensional. Two-dimensional, we can also solve straight up because we have variation of parameters. So if you want to, well, constant coefficient, okay? Anyway, well, I mean, even if it wasn't constant coefficient, you could still go through this, but let's keep it constant coefficient to keep it simple. But you know, if y1 and y2 are the homogeneous solutions, then we know by variation of parameters we have this formula. So you can rewrite this, and after a little bit of straightforward calculations, you get to, come on, you get to this. So basically, to find the solution, if you have this force, you're solving L of y equals to that force. What do? Well, you integrate that force with respect to this Green's function, and out pops the solution. So that's the inverse operator. So you can derive the form of the Green's function using variation of parameter in this time. The general problem is, so for an arbitrary differential equation, how do we find this inverse operator? Or in other words, how do we find a Green's function that we can take the integral of the Green's function times the inhomogeneous term and so generate a solution to the differential equation? This, it turns out, ties into the discussion of distributions. To really understand this, distributions come up. And so, of course, also transformations come up. So we've already started to talk about, I think I talked about Laplace transforms in here a little bit before, right? So jumping back to that again, if we take the Laplace transform of this, right, we switch over to the frequency domain, we can solve for big Y, take the inverse transform, and you've got that, right? So it's going to be the convolution of the inverse transform of this with the inverse transform of that. Of course, the inverse transform of big F is little f of t, the given force function. So you see the convolution of this thing, the inverse transform of that, which is called the transfer function. Well, this is the transfer function, I think, in engineering. The inverse transform of that is h. If you convolute h with your force, that gives you the solution. So if you look at that, it's again a Green's function. See, because I mean, essentially, this is a shorthand notation for a particular integration. Yeah, so you can look at that and find a Green's function from that if you unravel it. Let's see. Here's the proof that the property of the convolution. I'm deriving the convolution here. I'm trying to justify why the convolution formula is what it is on that page. And so there actually is the formula straight up. The Green's function for this problem is actually the inverse transform of the transfer function evaluated at t minus u. This is how to solve, the nth order problem. You just find the transfer function, find its inverse transform, and convolute it with your function. That's the solution. So, this starts to get much more interesting as you study so-called, well, here's an example. Here's a specific example of one. Here's another specific example of one. I'm just deriving the specific Green's functions for a couple examples because I wanted some examples. Here's more examples. More examples. I guess that's it. So anyway, what I'll talk about, I think I'm going to talk about distributions next. I'm itching to get the Fourier transforms because I really want to talk to you guys about Fourier transforms, but I'll do that after so chapter 6 is on distributions. So distributions are generalizations of functions, and it turns out to really understand the Green's function story, it ties us into the discussion of distributions. Although I think to understand the distribution story properly, we also need Fourier transform. I'll come to terms with it next time I teach. Anyway, thank you for bearing with me and giving me extra time today. I do appreciate it. Sorry, Audric. Hey, wait a minute. You can be watching. This is double speed. Why am I apologizing? I hope you ran well today. Talk to you later.